In this video, I will continue our discussion from the last video on the cumulative distribution plot and demonstrate how to, from our mean and standard deviation, derive the normal curve for this data set and compare the actual data to a normal distribution. And we can talk about some probabilistic behavior. So for starters, before we do anything else, we notice that this graph doesn't have any axes. So let me show you how to do that. First thing to do is to click on the graph and then come over here in Chart Tools and click on Layout. Under Layout, axis titles are conveniently hidden, and we can put a title below the x-axis, and like good engineers we will label it and put units, and so this is case weight in grains, and then we'll add a vertical axis. And generally we want a rotated title on the vertical axis so it looks nice and professional. And this is the frequency, or the probability as we generally know it. So in other words, we can directly read off measurements from our data set and look at probabilities. Now, according to our data set, we can see again that our 50% value is about 196, maybe a little bit more. In other words, 50% of our data is at or below 196 grains. So if I wanted to simply say, okay, well, how much, what are the chances that if I pick a single case out of that sample, it'll be between 195 and 196 grains? We can do that simply by saying, well, the probability that it's at or below 195 is about 25%. The probability that it's at or below 196 is roughly 50%. So there's about a 25% chance that if I pick a case out of there, it will be between 195 and 196 grains. This is useful, as we'll discuss in the next video, for deriving some physical meaning out of the data. Now, what if I wanted to derive all of this relationship without actually dealing with the sample data? Or, more importantly, what if I want to talk about a population that's not necessarily exactly the sample? Well, we can do that. We use what's called the standard normal curve. Now, this might be normally distributed, and we can find a normal curve about this, but the standard normal curve uses a mean of 0 and a standard deviation of 1. So what we need to do to compare our data to the theoretical model is we need to express the distance of the data instead of simply subtracting the data value from the mean. We need to subtract that data value from the mean and then convert it to standard deviations. So let's start that. Now, for reasons I'm going to explain here in a bit, we're going to start in column E instead of in column D. And we're going to say, okay, well, what is the distance of this point from the mean? We can see it's about -3-ish. So what we want to do is simply say this is equal to our data point minus our mean. We see that, and that is unfortunately still in units of grains. The standard normal curve doesn't have units, it's unitless. It's in units of standard deviations. So we need to convert that. So if we want to go from grains to standard deviations, we happen to know that one standard deviation is equal to 1.74 grains. Conveniently, we've already calculated that. So to convert from grains to standard deviations, all we need to do is divide by this number. Now, we see that we are 1.85 standard deviations to the left. That makes sense. Almost 2 standard deviations gives us about 3 grains. And so we see that relationship pretty easily. Now, we need to fix this because I want to drag this down as I did in the last video. So we need to fix these values such that as I drag that down, it doesn't try to reference values that are blank below it. In other words, as I drag this down, it's going to want to change G2 to G3 and G3 to G4, etc., etc. To fix that, we put a $sign in front of the row number. Now, if I grab this and drag it down to the bottom of my data set, we should get the deviation from the mean of all the data points. And we see, knowing that our data set is somewhat symmetrical, we see that we go on the right 1.83 standard deviations to the right of the mean and 1.85 to the left. So already we can see that our data is evenly distributed about the mean, at least at the extreme ends of the range. And so we're going to call this column Z. Traditionally, Z is equal to the deviation of the data in terms of standard deviations. So the way to read this is that 192.9 grains, this data point, is 1.85 standard deviations to the left, hence the negative sign, of the mean. Because of that, it's very important that this subtraction maintain the correct order. In other words, we need to subtract the data point minus the mean, and in all cases that will keep the negative correct. Okay, so what we actually want to do is see whether the normal distribution matches our distribution, our actual data, and then what we really want to do is be able to reference the normal standard distribution, this standardized function for which we have lots of probability tables already integrated and built-in functions to Excel, such that we don't have to construct these really complex plots, especially if we want to talk about the way that a population performs. Our sample data isn't necessarily the best representative for that. So we could type norm dist. Of course, if you're going to type in a function in Excel, you need to start with an equal sign. And if you type a function and open the parentheses, it gives you the arguments that it asks for. If we wanted to fit a normal distribution to our data, in other words, I want to put a normal distribution on these axes that makes sense, it needs the data point that I'm referencing. It needs the mean of the data set, the standard deviation of the data set, and what kind of normal distribution I'm talking about. Is it cumulative or is it symmetrical? So we don't want to give it all that information. That's very complicated. So what we'll use is the normal standard distribution. All I need for the normal standard distribution is the deviation of each data point from the mean in terms of standard deviations. We calculated this in this column Z. So all we need to type is a reference to that column, and we see that the normal distribution, the theoretical model, is predicting that 3% of our data should be at or below 192.9 grains. Funny, about 3% of our data is at or below this point. So if we were to drag this down and fill in this column with data, we see, lo and behold, we're about symmetrical. We've got 3% hanging off the top and 3% hanging off the bottom, as expected because our actual deviation was nearly exactly symmetrical. And, just as a verification, we know that the normal curve should have exactly 50% of the data to the left of the mean. So if we come over here into our data column, remember this is the one that's sorted, and we come down here to 196.1 grains, we see that 50% of our data is to the left as we pass that point. So what this tells us, and we're going to go ahead and label this as the normal frequency in percent, what this has calculated is the predicted behavior according to the normal curve. So here we've got our actual data, and here we've got the predicted data. So we want to see how accurate these are. So what we need to do is add a data set to our chart. So you right-click in the chart area and click Select Data. Now we want to add a series. And to select from the table, you simply click on this button here, and these are the X values. We want the X values to be our sorted case weights, right? And click this again to go back. And the sorted Y values, you need to delete these 3 characters and then go select your Y values, which is the normal frequency. And click OK, and we can see it's already been plotted. This red line is the theoretical model. The blue line is our actual data. We can see right away, as we pretty much expected, our data is almost perfectly normally distributed. It's very, very close to a normal distribution. We see some deviations here and there, but for the most part, it's really not a problem. One obvious thing is we have, in some areas, measurements that are exactly the same. This is indicative of an instrumentation system that doesn't have enough resolution to describe the phenomena that we want to look at on the scale that we're looking at it. Here it does a pretty good job because we've taken quite a few data points. But if we have severe resolution problems, you'll turn up with probability distributions that aren't very descriptive. So in a lot of situations we have to keep an eye on instrumentation and resolution. But this is very useful. In other words, what we can do is we can look at the normal distribution, and anymore, because we know that these two are very accurate, I don't have to calculate an actual frequency anymore. All I need to do is take my data, calculate the mean, and the standard deviation, and I can derive probabilities from that. In the next example, we'll go through a real-world example of where tolerances matter and how that figures into probabilities and product cost.